We have discussed how the thermal conductivity of an insulator arises from phonon scattering, and we have considered in the last lecture the temperature dependence of the thermal conductivity of such an insulator and compared it with that of a metal. I would just like to mention at this point an important point regarding the nature of phonon scattering in contributing to the thermal conductivity of an insulator. If you have a perfectly harmonic crystal, the phonon states are stationary states. If a phonon distribution carries a thermal current, then that distribution will remain unaltered in course of time, and the thermal current will remain undegraded forever. In other words, a perfectly harmonic crystal will have infinite thermal conductivity. However, the thermal conductivity of a real insulator will be finite for the following reasons. One, the inevitable lattice imperfections which act as scattering centers for the phonons, thus causing the thermal current to decay in time. 2, the scattering at the surface of the solid, and 3, the approximate nature of the harmonic potential and the stationary states of phonons. If the full unharmonic Hamiltonian is considered, a definite set of phonon occupation numbers will change in course of time. This again will mean that the thermal conductivity becomes finite. So, unharmonicity is the key to understanding the behavior of thermal conductivity of solids. This is an important point, because we now pass on to consider another interesting property of solids and liquids. This is thermal expansion. We all know that when a material is heated, it expands usually. In other words, its dimensions increase. Thermal expansion is a measure of the increase in length of the material due to a rise in temperature. This expansion is measured by the coefficient of linear thermal expansion, which is defined as the increase in length per unit rise in temperature with respect to the unit length of the material, per unit length of the material. Well, again the expansion of solids on heating is a direct consequence of unharmonicity in the vibration of lattice atoms. For example, let us consider a one dimensional solid for simplicity. If the vibrations of the atoms were perfectly harmonic, the potential energy will have the form V of x equals half f x square, where f is the force constant. Since this potential energy is proportional to the square of x, the curve V of x, if it is plotted, it will be a parabola. So, x naught is the equilibrium position, the harmonic vibrations around this will create a perfectly parabolic shaped potential function. In such a harmonic potential, the mean position of the oscillator does not shift with increasing temperature. This can be proved readily by calculating the mean displacement x bar, which is given by x bar equals integral x exponential half f x square by k b t dx by and this will turn out to be, if it is evaluated, shown to be vanishing. So, there is no change. Now, you can also see this by looking at the graph here, which portrays figures, which portrays the interatomic potential as a function of the interatomic distance, and you see that you have these various states here, and these, when there is an increase in temperature, vibration amplitude changes, but as long as this remains harmonic, the center of this will be the same, the equilibrium position does not change. In other words, there is no shift and there cannot be a thermal expansion. It is only when there is an unharmonicity or a departure from harmonic behavior, it is then that this curve will start looking like somewhat like a deviation from parabolic behavior, and then the mean position will start shifting like this. So, there is a net shift of the mean position x bar and with an increase in temperature. So, this corresponds to states of different temperatures, and the mean position shifts like this. So, this gives rise to a thermal expansion. So, this is a pictorial explanation. The atomic oscillators, when they are not perfectly harmonic, can be written by a potential function which is not just a half f x square So, these are the unharmonic terms. So, when you include them and calculate this integral, we can perform this calculation. So, let us take this. So, we can show that x bar is 3 g by f square k b t. We can, I show the calculation in the transparency. So, you can see that x bar is written like this: x exponential the unharmonic potential divided by k b t, negative of that, dx, and denominator you have the same integral exponential, again the unharmonic potential minus negative of that by k b t dx. If you calculate that, first of all we notice that for small unharmonicity, the terms exponential g x cube plus h x to the power 4 can be approximated by 1 plus g x cube plus h x to the power 4. So, if I have k b t, this will be so that we can use this and calculate the rest of the integral, and this leads to an expression of the form integral g x cube by Gx to the power 4 by kBt exponential minus fx square by 2 kBt dx divided by this will, by suitable substitution, this can be shown to be equal to 4 kBt by f square times gamma phi by 2 by gamma half, where these are the gamma functions. That would give you the result 3 kBt So, you can see that there is a net change, a non-zero mean displacement in the presence of the unharmonicity, and that is what contributes to thermal expansion. So, you can see that the energies, there is a shift, and the mean displacement is directly proportional to the temperature, and it is also directly proportional to the coefficient G, the unharmonicity coefficient, but is inversely proportional to the square of the force constant. If you have a solid which is strongly bonded, for example, covalently bonded solids or very strongly bonded, diamond is an example, the force constant will then be very high. So, the mean displacement and hence the expansion coefficient will be very small, whereas in weakly bonded solids the force constant will be small, but the coefficient G will be higher. Therefore, the mean displacement is large and hence the thermal expansion coefficient will be higher. So, covalently bonded solids like diamond and silicon have very low thermal expansion values. Polymers such as rubber and perspex have much higher coefficients of thermal expansion. In the case of metals, the thermal expansion coefficient lies between the values of solids like diamond and silicon on the one side and rubber and perspex on the other. So, the thermal expansion coefficient of some of the typical materials which are commonly used are all shown in table. You can see the values given for materials like aluminum, copper, silver, alumina, concrete, glass, perspex, wood. You can see the thermal expansion coefficient is also, along with this, the specific heat and thermal conductivity values are given. So, together these give you the entire spectrum of thermal properties of So, we have considered all the thermal properties such as specific heat, thermal conductivity and thermal expansion coefficient based on our understanding of phonon states, phonons and as well as electrons. What is now left is only a discussion of the temperature dependence of the electrical conductivity. Of metals. This is a very important property, so we would like to discuss this at this stage. We will consider this in detail in the next lecture, but at the moment I will give a brief introduction to what is happening. Now, we are equipped with all concepts about phonons and electron gases. In a metal, as we know, it is the electron gas as well as the phonon gas which give rise to scattering processes which take away the electron carriers, the charge carriers from their normal trajectories under the influence of an applied electric field. So, the current density decays. So, it is these scattering processes, scattering of electrons by phonons, this is what is at the bottom of the temperature dependence of electrical conductivity of metals. So, the Drude theory, the simple Drude theory which we have already considered, gives the expression for the electrical conductivity Drude expression. In this, N is the concentration of electrons. Of course, the Drude expression is a very general one, not only valid for metals, but in general for any material, but we are now applying it to the case of a metal. Now, we know that the concentration of free electrons which are responsible for conductivity in a metal are constant, they are not dependent on the temperature, M and E are also constants. So, the entire temperature dependence is due to the temperature dependence of the relaxation time tau. So, the key to understanding the temperature dependence of the electrical conductivity of a metal is contained in an understanding of the temperature dependence of the relaxation time for this is the relaxation time for electron phonon scattering. There is also scattering by impurities, any kind of impurities. So, both processes of scattering give rise to the relaxation behavior and hence contribute to the conductivity. However, if we have, for example, a perfectly periodic pure solid, then there will not be any scattering even at a finite temperature, and therefore, there will not be a temperature dependence here. So, it is the scattering processes due to deviations of this perfect periodicity due to the presence of different kinds of impurities like point defects, vacancies, interstitials, dislocations, grain boundaries, stacking faults, all this will contribute to impurity scattering. But this impurity scattering is not temperature dependent, it is something which is constant. So, it gives rise to a temperature independent in terms of, we will speak in terms of the reciprocal of sigma, namely the electrical resistivity. So, this gives rise to a temperature independent resistivity, whereas the electron phonon scattering gives you the temperature dependent resistivity. So, that rho is rho naught plus rho 1 T. So, this is due to impurities and this is due to phonon scattering. So, the total resistivity and its temperature dependence is determined by this. We will now discuss the temperature dependence of electrical resistivity of a metal as we already pointed out, this temperature dependence arises from the scattering of the electrons, the so called free or conduction electrons, by phonons. To discuss this, let us write the periodic potential of a rigid ion lattice. Now, this is given by, let us write this as U periodic, which is a function of the position coordinate r of the atom in the lattice, which is a summation over all the lattice sites of the potential at any given lattice site over all the Bravais lattices R. This is well known, but this is only approximate. Because actually the ions are not rigid in the lattice, and we actually have the actual potential is really a sum of these individual atomic potentials, which are a function of not only this, but also where U, well, let me write this as capital U to distinguish this from the displacement. From equilibrium position. So, strictly this can be written as the U periodic, this one, minus sigma over R U of R dot the gradient of the potential del V of R minus R plus higher order terms. That is the expression. So, the difference between the actual potential and the periodic potential is a kind of perturbation. This is a perturbation which acts on the stationary states of the periodic Hamiltonian. Now, which will give block levels. So, we have this perturbation causes transitions among the block levels, which are the stationary states of the periodic Hamiltonian. This is what causes degradation of the electric currents, which otherwise would be infinite. So, this is the mechanism for how we get a temperature dependent electrical resistivity due to the degradation of the electrical currents, which arises from this perturbation, which is due to the electron phonon interaction. So, for the phonon scattering, as we have already discussed, we have it is an elastic scattering. So, which should satisfy the relation So, this is a energy conservation, q is the phonon vector. So, the real situation, this is a constraint, an equation which constrains a two-dimensional surface. So, this defines a two-dimensional surface of allowed wave vectors, allowed by the conservation condition. Wave vectors q in the three-dimensional phonon wave vector space. So, that is the mechanism, and figure shows the electron phonon scattering event, which can be described in the Fermi surface. This is the Fermi C, and we have a state with k wave vector k being scattered onto a state of wave vector k prime, such that k, which is k plus q. So, that describes the conservation situation, energy conservation. So, that is the event, and this angle theta is the scattering angle. So, that is the whole picture of how a temperature dependent electrical resistivity arises from electron phonon scattering. Let us look at this situation at different temperatures, because we want to discuss the temperature dependence. First, let us consider high temperatures. So, temperatures which are high in comparison to the Debye temperatures. That is the first limiting situation. In this, for any normal mode, the number of phonons n of q is given by 1 by e to the power h cross omega q by k b t minus 1, since the phonons are bosons, and when the temperature is high compared to the Debye temperature, this can be written as so the number of phonons increases linearly with T. For any normal mode q. So, if the number of phonons increases linearly with temperature, so does the electrical resistivity. At such temperatures, the scattering, so the electrical resistivity also increases linearly with temperature at temperatures large, at high temperatures compared to the Debye temperature. Now, what happens at low temperatures when the temperature is small in comparison to the theta d? This is high temperatures. So, at low temperatures, we do not have enough phonons to scatter the electrons. Only phonons with energy h cross omega q comparable to or less than kBt, they will be emitted or absorbed by the electrons. So, when this is the condition, then in this domain we know that the dispersal relationship is of this form, omega equal to Vq, where V is the speed of sound. In the medium. So, that Q is of the order of kBt by h cross V. That is the condition for the phonon wave vector. So, only within the surface of phonons that the energy conservation law permits, only a subsurface of a linear dimensions proportional to T, and therefore, surface area T square linear dimensions is proportional to T. Therefore, surface area is proportional to T square can actually participate. This is shown in the next figure, where you have a wave vectors of those phonons allowed by the conservation laws to participate in a one phonon scattering event with the electron whose wave vector is k. So, this is shown in this figure, and therefore, the number of phonons decreases as T square because of this. Now, the electron scattering rate actually declines faster than this. This is because we have the electron phonon coupling constant whose square is given by well, I am stating this without proof, this is a standard result. Into half h cross omega q k prime. Well, let us write just k minus k prime. Here k naught is the so called Thomas Fermi wave vector. Which is defined by k naught equals 4 pi E square dn naught by d mu. Because of this, the consequence is that this matrix element coupling constant g k k prime is such that when k minus k prime is small at low temperatures, then the coupling constant, the square of the coupling constant, is proportional to k minus k prime. And therefore, this is of the order of kBt by h cross omega. And therefore, this decreases with temperature linearly. Therefore, for T very small compared to theta d, the electron phonon scattering rate decreases as the cube of the temperature. However, we also have to consider an extra factor in this situation, that this one phonon process, which is due to an elastic scattering, only favors the forward scattering in the forward direction. Elastic scattering with only a very small change in the wave vector favors scattering in the forward direction. So, this can be shown to be taken into account. The preferential concentration of the scattered phonons in the forward direction can be taken into account by considering an effective scattering rate which is an angular average over all scattering angles theta weighted with a factor p of theta equals 1 minus cos theta. And now, this factor p of theta is 1 minus cos theta is really 2 sin square theta by 2, and you can see this situation here. So, this is really half of q by kf square, where kf is the Fermi wave vector. So, this again gives you a t square. So, this gives you another t square dependence. So, that combined with this t cube dependence, the net t to the power phi dependence, there is a t to the power phi dependence of the scattering rate and therefore, the resistivity at low temperatures. The situation can be rigorously discussed It has been done by Bloch and Gruneisen. They discuss this situation theoretically for all temperatures. Now, this leads to a rigorous expression which gives the electrical resistivity as integral 0 to x e to the power z minus 1 to z to the power phi dz by 1 minus e to the power minus z. Now, this leads to a lattice resistivity rho L which goes as 4.225 evaluating this integral T by theta d cube of phi into j phi of theta d by t times the resistivity at the d by temperature, where j phi of x is this integral. So, this gives you the actual Bloch-Gruneisen law for the phonon resistivity rho L, which is depicted in figure as a relation between the reduced resistivity rho of t by rho of theta d as a function of t by theta d. So, this goes, this is a linear relationship for large values of t by theta d, and then it becomes nonlinear and goes like this. So, this is a behavior which has been experimentally observed for a wide variety of metals like gold, sodium, copper, aluminum, nickel, and by fitting the actual measured temperatures to a theoretical expression like this, you can actually obtain a value for the d by temperature and compare it with values deduced from specific heat measurements. However, this discussion has not taken into account Umklapp processes, considered only a normal process, but as we know from the thermal conductivity discussion, Umklapp processes are quite important, and also a possible non-spherical Fermi surface. We have considered only an isotropic spherical Fermi surface. So, these are the two factors which have not been taken into account, but these effects are not dominant in the alkali metals for which the Bloch-Gruneisen law has been verified by the experimental results. Now, this I have given some references for this discussion, particularly Ashcroft, the textbook by Ashcroft and Mermin, and the book by J.S. Dugdale, which I already discussed, Electrical Resistivity of Metals and Alloys, and also Feng, Condensed Matter Physics, which is a world scientific book. So, these are discussing some of the salient features of this Bloch-Gruneisen theory.